Hello, this is Minji from Human-Centered Computer Systems Lab in Seoul National University. I will present our paper, Bubbleu Exploring Augmented Reality Game Design with Uncertain AI-Based Interaction. Object detection technique has a large potential as an AR game interaction method. By detecting various objects in the scene, the game system could combine the virtual contents into the real world regarding the context and could implement tangible interaction in diverse environments. However, object detection has a critical limitation in that the results are inherently uncertain. This problem is due to the statistical nature of the AI inference. Technical improvements do increase the accuracy, but we could never guarantee that it would be always right when the input is far from the dataset. When we perform object detection, we will notice various errors like in the left figure. Here an apple and a banana are correct, but the donut is misclassified as an apple. And the unstable scenes such as occlusion, motion blurs, or unusual angles often cause even higher error rates. The errors in the interaction would lead to a huge degradation of the game experience. So we chose a new approach. We focused on the characteristics of games. We started with the idea that we could design a game in which the player would naturally overcome the errors, like in this figure, telling them that an error might have occurred and asking them to fix it. Our key approach is that a careful game design would deliver a nice player experience even with the errors, because the experience is affected by multiple factors other than the accuracy. We've decided to investigate how to design games to handle uncertainty and give a better experience. So this is our overall study process. First, we conducted a pre-design study to explore the design space of various AR games. Then we designed a game to be investigated, named Bubbleu, and implemented the baseline version. After playtesting Bubbleu, we conducted a design improvement workshop and generated 3 improved design candidates. Finally, we ran a user study to investigate how the different designs affect the user experience. This is how Bubbleu plays. Bubbleu is an AR pet breeding simulation game. The player can interact with a virtual pet by manipulating diverse real objects. Bubbleu provides 3 types of interactions: feed, watch, and play. The baseline Bubbleu played well, but the errors in object detection disturbed the gameplay a lot. We improved Bubbleu in 3 ways by adding different error handling features based on 3 design concepts: ambiguity, transparency, and controllability. The ambiguity version utilizes high-level expressions to hide minor errors. When an error is expected, the pet shows an ambiguous eat icon instead of the specific food icon. This could hide minor errors such as misclassifying an orange to an apple like in the right figure. The transparency version reveals more information about the detection result by showing an additional UI during the interaction. When an error is expected, the pet gives an additional guide such as please move the camera around slowly so that the players can notice the error and fix their behaviors. The controllability version has a special feature. When detection fails, the player can use a hand gesture to temporarily increase the sensitivity of the detection. By doing this, the chance of detection increases, but the chance of the error would also increase. After implementing 3 candidates, we conducted user study experiments to investigate how this design changed the user experience. We recruited 36 participants and divided them into 3 groups of 12. Each group played one of the improved versions along with the baseline in a counterbalanced order. For each version, we had 2 types of experiments. The first one is a free gameplay study. We investigated whether the designs affect the error rate in the natural gameplay. The second one is a controlled gameplay study. Here, the participants were given a set of interaction tasks, and some of them contain manually injected errors. We investigated whether the designs affect the perception of the errors. And at the end of the study, we conducted a comprehensive interview to ask whether the participants preferred the improved designs over the baseline. The 3 design candidates chose different results in both success rates and perceived error rates. The left chart shows how much of the interaction attempt in the free gameplay was successfully done without error, and the right chart shows how much of the injected errors were perceived during the control gameplay. The ambiguity version showed a large improvement both in increasing the success rate and decreasing the perception of errors. Especially, the success rate would increase by about 20% point to the baseline. The transparency version also improved the success rate, but resulted in a high rate of perceived errors. The additional information enabled players to modify their behaviors to make clear detections, but the information also led them to be sensitive to the errors. The controllability version showed minimal improvement in both the success rate and the perceived error rate. Interestingly, when we asked the participants whether they preferred the improved design over the baseline, the result was the opposite. Only 4 out of 12 participants answered that they like ambiguity more than the baseline despite having the fewest errors. Most of them reported that the ambiguous interaction confused them when they were expecting other interactions. The other 2 designs were more preferred than the baseline. In transparency, 9 out of 12 reported that they would like to have more information and guidance. It was impressive that all the participants of the controllability group preferred the design. Some of them mentioned that missing detection is very annoying, that they would like to have a chance to at least start the interaction even when the result would be uncertain. So we conclude our study like this. Ambiguity had explicit improvements in error rates, but the expression often confused the players. We recommend designing ambiguity carefully to give a positive experience while hiding the errors. Transparency resulted both in high success rates and high preference. Giving more information can help the players to understand and overcome the errors. Controllability was highly preferred by the players. Providing controllability would give a positive experience, though it would have a low effect on decreasing the errors. In future works, we would investigate the effects of the detailed parameters within the design, such as which specific detection threshold preserves player experience the most. Or in another direction, we would explore the generalized error handling methods to the diverse AI inferences. So this is the end of the presentation. Thank you for listening.